Good evening, ladies and gentlemen. The management is proud to present FX and FOBS from Resecurity Labs, ready to school all y'alls on port scanning. Give them a big round of applause right now, FX and FOBS from Resecurity Labs.
Thank you. Okay, I feel like having a déjà vu. I've just been here. Anyway, port scanning improved. You're not going to listen another hour to me. I'm just having the intro slides. First question, why should we reinvent the wheel? Why should we write another port scanner? Yawn. The world changes constantly. Essentially, the world also is full of crappy software. And the requirements for software also change. And when the requirements change sufficiently, it's time to write new software. Because the software no longer fits the purpose it had to begin with. Some software actually never fit the purpose it had, but that's a different story. Now, reality is your measure. What I'm trying to advocate here is redo software. There are times when you need to drop whatever you used so far and write it new. It is only something for people that have a realistic chance finishing the project, because the crappy original is still better than the unfinished sequel. You should actually go ahead and extrapolate. If I start solving this problem correctly in contrast to what I'm using so far, and it's going to take me infinite time, is the problem in infinite time going to get worse or better without my solution? If it's going to get better, wait. You can use your time for other things. Go party, go drink, whatever. Wait, someone else is going to solve your problem. If it's a performance problem on a computer, for example, wait. Intel is going to take care of that. Second rule, don't make a schedule. Because the first piece of software grew over years and years. Yours is not going to be perfect right away, but make it as good as you can. And then set your requirements. Remember, those are your requirements. We had this issue with the port scanner all the time. Don't try to please everyone you talk to. Everyone came like, okay, so you're writing a port scanner. Is it going to do fingerprint, foobar, nmap, blah, blah? I'm like, no, we're writing a port scanner. We're looking for open ports. Don't import requirements from the existing software. Just because you're replacing something, it doesn't mean you have to implement all the features it had, because the features might not have been that useful to begin with. And if you need that feature in the future, you can implement it later. Don't read too much code of the other solution, because at the end of the day, your thought process is going to be as crude as the code you're trying to replace, and nah. We know how that looks like, BSD, Apple, the whole story. Now, there are people who say, well, why should I do that? That's uncool. If you want to research quantum cyber cryptofeminism and its impact on onion routed RFID 6.2.0, go ahead. We're not saying everyone should do that, but there are times when you actually have to step back from the real cool things and do some work. Because that's what port scanning is for us, work. For most people, port scanning is fun. They find open ports, they get root shells on systems they're not supposed to have root shells on. They need random scanning. They need like lead output. They need 23 different scanning mechanisms to get around IDS systems. But for us, port scanning is work. We need accuracy and we need speed. Because speed translates to the time you're sitting at the customer's place, which translates to money. And we will use dedicated machines. We will not porn surf at the same time with the machine. We're not going to chat at the same time with the machine. We're not going to play Doom at the same time with the same machine. We're using dedicated machines for that. Just to be totally clear, hats off to Fyodor, definitely, because if you have lived in the times before Nmap and you've used like SynScan or ConnectScan or other crappy tools, you loved Nmap. And I really don't miss the times before that. And it introduced many important inventions that may not belong to a port scanner, but hey, things grow. And redo software in general doesn't mean that the original is bad. It just means you need something else. Now, why could we not work with Nmap? The initial trigger for saying, okay, let's write our own port scanner, was port scanning larger networks. And I have to confess, I'm coming of age. There's only so many times per day I can jerk off. And it's not appreciated at the customer side anyway. So waiting for my port scanner to finish to actually start penetrating systems sucks. And the scanner is not lead if it takes 13 minutes and 37 seconds per host. So in a professional environment, you don't port scan systems that are not there. They're powered off, disassembled, carried around the office, thrown away. And when you map large-scale networks, you don't care about this one machine that has the one weird port open somewhere up there in the port range. You care about the big picture in linear time. So on a more abstract level, all the cool features that Nmap has, all the fingerprinting, all the foobar, depends on one single piece of data, which is a list of open and filtered ports. Ever noticed if Nmap doesn't find an open port, all the fingerprinting and everything else goes boom? That's the reason. So we essentially concentrated on getting this list. So our requirements were TCP SYN scanning only, no Christmas trees, nothing else, no UDP scanning, because in a modern world, UDP scanning has zero value. The port is either firewalled or open. In both cases, you don't get an answer, because UDP is a negative scan. It will only produce an answer, named ICMP port unreachable, if the port is closed. Now those cases are gone. We need constant access to result data. We don't want to wait for Nmap to finish and then see what we got. And we use it in dedicated boxes that essentially the idea was get a black box, put the scanner in there, feed it what networks to scan, ship it to the customer, tell the customer, you see, there's a box, plug it in, when it stops blinking, send it back. Bottom line, we wanted a port scanner that does exactly one thing and does it right, which introduces Port Bunny and FOBs, the author of Port Bunny.
Hello. Now that you've heard all about the requirements, let's just see what we made of that. And what is so different about our new port scanner, Port Bunny. And to start off with, Port Bunny does something really funny. It actually sends more data than it would have to perform a complete TCP SYN scan, and still gains speed on the long run. Secondly, Port Bunny builds a bridge between TCP congestion control and port scanning. And I'm quite aware of the fact that TCP congestion control is not the kind of term you hear every day, and it's certainly not as catchy as Web 2.0. So don't worry about this. We're going to go into this. And most of all, what Port Bunny showed me was that even a simple problem such as a vanilla TCP SYN scan can be extremely complicated if you really want to get it right. Okay, so before we go into all these details, let's just go over the basics real quickly. So if you're going to want to port scan, of course, you want to know which ports you can actually connect to. So what you do is basically you connect to each port in a row. But not completely. You just send a connection request in the form of a TCP SYN packet, and depending on the answer you get, you can figure out if the port is closed, open, or filtered. So if it's closed, you will get a reset. If it's open, you get an acknowledgement, and if it's filtered, and that is something that is often overlooked, you won't get any response. So those are the basics. And that looks pretty easy, so you'd be thinking, what's the problem? Why can't we just, wrap a send call into a for loop and, just wait for the responses and, yeah, then just output the results. Well, that won't quite do it because if you just send as fast as you possibly can, what will happen is the network will just start dropping your packets randomly, and you may even cause a congestion collapse, which means that you're going to be waiting 2 seconds until anything else happens again, or something like that. And that, of course, means, if packets are randomly dropped, then you're going to report many ports as filtered, which are actually not filtered, but, the packets were just dropped. And there's another important thing here. There is some kind of optimal speed that you want to find, but this optimal speed, it will change over time, because you are not the only person who's using this network. Other people may be using it, and so you will have less capacity depending on if somebody's starting a big download or something like that. So naturally, the question arises: can the network actually tell us to slow down? And the general answer is no, it can't. There are some exceptions, but they are seen very rarely. There are ICMP source quenches, and then there's ECN for IP version 6, but that's really academic. You don't see that in your everyday network. So the answer is no. The network will just not tell you how fast you can scan. So what info do we have? Well, if you do receive a response for one of your probes, then you'll have a round-trip time. That's clear. What about packet drops? Well, if you're absolutely sure that the packet you sent should actually generate a response, then of course if it doesn't, then you can detect a packet drop, but only then. And if you remember, if you're performing a normal TCP SYN scan, you can't know if the port may just be filtered. So if you don't get a response for that TCP SYN probe, then you don't really know if the packet dropped or if the port was just filtered. So that's all the info we have, just round-trip times and possibly packet drop detection. Okay, so let's step back a little bit and see how a network model would look like. What environment are we actually playing in? Well, we all know it's a network, so we're not directly connected to the machine. There are a couple of nodes between us, and all these nodes have a queuing capacity, which means that they can save the data and don't have to send it on straight away. And the nodes are connected through different links of different quality. There's the throughput characteristics, delay, and reliability, basically. So one tends to think of this simplified in this way. This probably comes from socket programming. You tend to think of it as a point-to-point connection between two computers. And the term bottleneck basically suggests that there's one thinnest connection that all data has to pass. But that's basically, the simplified model you would have. So to regulate speed, to find the optimal speed would mean to find the optimal delay between two packet sends. So that might look something like that. So much for theory, but in practice, finding this optimal delay will fail. And that's the first thing we had to learn the hard way. Because, number one, there's a so-called round-trip time problem, which means that you only know if a packet dropped after a complete round-trip time, which means that once you detect the packet drop, you've already sent all those blue little packets there, and they will hit the bottleneck and cause a congestion collapse. And that's a big problem. And then there's a second problem, and this is far more important.